Hello everyone, and welcome back to Byte&Cache. If you are new to the channel, we specialize in the mechanics of artificial intelligence, so you can apply these systems to your own business operations. I recently completed Google's 5-day AI Agents intensive course, which detailed a transition in how these models are built. We are moving from passive chatbots, tools that wait for a prompt to generate text, toward autonomous agents that can independently plan, use software, and complete multi-step projects. When we remove the requirement for a human to mediate every individual step, the role of a manager changes. Instead of supervising a conversational co-pilot, teams begin to oversee an agentic workforce that executes entire workflows. This shift is already visible in systems like Google Coscientist and AlphaEvolve. Coscientist bridges the gap between digital reasoning and physical action. It searches the internet for reaction data, writes the code to operate robotic laboratory equipment, and physically runs experiments with minimal human intervention. AlphaEvolve applies a similar autonomy to software engineering. It creates a piece of code, evaluates it against the current version, and keeps the result only if it is more efficient. It continuously and iteratively mutates its own search spaces to optimize cloud infrastructure without a developer in the loop. These systems demonstrate that AI has moved from a static lookup tool into a self-improving executor of complex tasks. But how does a closed AI model actually know how to interact with an external business program, like a calculator or a calendar? Engineers use a concept called RAG for tools. A central AI node sends search pulses to a ring of software functions. Instead of searching a PDF for information, the agent queries a database of functional software and locks on to the specific API or calculator it needs for that moment. By retrieving tools only as they are needed, the agent remains lightweight. It doesn't need to have every formula hard-coded into its memory. It simply picks up the right tool for the job during execution. Supporting these agents requires a robust back-end architecture. Think of this assembly line as the data pipeline that feeds the system. Messy, raw data enters on the left and is processed into structured blocks on the right. During the extract phase, the system scrapes through a company's internal databases, spreadsheets, and emails to gather raw information. In the transform phase, the system cleans that data and converts it into embeddings, a mathematical language that allows the AI to understand relationships between different data points. Finally, in the load phase, these embeddings are stored in a vaulted vector database. This provides the agent with a long-term, secure memory it can reference instantly. To keep the agent's code updated without causing failures, developers use continuous integration. This is an automated testing layer that verifies every new code update before it is finalized. This is followed by continuous deployment, automating the delivery of the updated agent to live servers, ensuring the system evolves without breaking existing software connections. Without these pipelines, an AI agent becomes an amnesiac system, too fragile for enterprise use. Even with strong pipelines, the output of an AI model can be unpredictable. Deploying an unchecked update directly to users creates an immediate risk of system failure. To mitigate this, Google utilizes blue-green testing. The stable, current environment is blue. We deploy the new agent to an identical, hidden environment called green. We can then route just 1% of traffic to green to observe how the new agent behaves. Creating these twin environments manually is slow. Instead, engineers use Terraform, a tool for infrastructure as code. This allows them to write a script that builds an entire network architecture in seconds. Before a human ever interacts with the green environment, automated testing frameworks run hundreds of simulated conversations to check for hallucinations or logic errors. This strategy provides a failsafe. If the agent fails, we instantly route traffic back to the stable blue environment with zero downtime. Connecting an autonomous agent directly to corporate data introduces a vulnerability, the potential exposure of personally identifiable information, or PII. Here we see a governance shield using SIF to protect sensitive data from being scanned or leaked. SIF, or Sensitive Information Filtering, acts as an architectural layer that redacts or masks private information in real time before it ever reaches the core AI model. This ensures the principle of least privilege, where an agent is granted the absolute minimum data access required for its specific task and nothing more. We also implement complete audit trails to track every decision the agent makes, along with human-in-the-loop pauses for high-stakes actions, like executing a financial trade or sending a legal contract. Integrating strict SIF architecture and governance protocols is the necessary foundation for using autonomous AI in a professional environment. The transition from passive chatbots to autonomous agents represents a significant change in how business technology is structured. By utilizing RAG for tools, robust CI/CD pipelines, and SIF security frameworks, you can deploy these agents safely and effectively. If you found this breakdown of the Google AI Agents Intensive course helpful, please subscribe, give this video a like, and comment below with the agent capability you are most excited about. Thank you for watching. As you explore the recommended content on screen, remember, keep learning, keep innovating, and we will see you in the next video here on Byte&Cache. The infrastructure you build today determines the capabilities of your AI tomorrow. Build it correctly, and the agentic workforce is ready to execute.